Module 25, Lecture B, Spectral MDS TSNE. By the end of this lecture, you will be able to apply spectral embedding and MDS methods for nonlinear visualization, configure t-SNE perplexity, learning rate, initialization, and convergence settings, and evaluate manifold embeddings using trustworthiness and visual comparison. Spectral MDS. Spectral embedding. Spectral embedding reduces complex high-dimensional data by building a graph of nearby points and preserving their local relationships. Instead of relying on straight-line distances, it captures patterns that may lie on a curved surface. By analyzing the graph's connectivity, it creates lower-dimensional coordinates that keep similar points close together, making it useful for nonlinear data such as changing images or sensor readings. Spectral embedding uses eigenvectors, often from a graph Laplacian, to create new coordinates that reveal smooth patterns in data. By emphasizing local similarities, it can make hidden structure easier to see, such as clusters, transitions, or groups in complex data, like handwritten digits or social networks. Spectral embedding reveals nonlinear structure by using connections in a neighborhood graph, so its results depend strongly on how that graph is built. Too few neighbors can break the graph into disconnected pieces, while too many can make it too dense and hide important patterns. Choosing the number of neighbors and handling noise carefully are key to producing useful visualizations. As an exploratory tool, spectral embedding helps show how local relationships form larger structures in data. Python code, spectral embedding. Spectral embedding is demonstrated on curved synthetic data to show how neighborhood graphs can capture nonlinear manifold structure. The resulting coordinates unfold the data, with color used to indicate the transform's layout. This setup imports the main tools needed for a manifold learning example. NumPy supports numerical work, Matplotlib creates plots, and the Scikit-Learn version can be checked for compatibility. From Scikit-Learn, the S-curve dataset generator provides synthetic data. Spectral embedding reduces its dimensionality while preserving structure, and the trustworthiness measure evaluates how well local neighborhoods are maintained. We generate a synthetic three-dimensional S-curve dataset with 600 points using the make S-curve function. A small amount of noise makes the data more realistic, while a fixed random state ensures the same result each time. The output includes the point coordinates and a color position array used to visualize each point's location along the curve. Before spectral embedding, the code verifies that the dataset contains 600 samples with 3 features each. If the shape is different, it raises an error to signal that the data is not in the expected format. This check helps prevent problems during the embedding process. A spectral embedding model is used to reduce the data to 2 dimensions while preserving its main structure. It builds the embedding from local neighborhood relationships, using 12 nearby points for each data point, and a fixed random state keeps the results reproducible. After fitting the model to the original features, the data is transformed into a lower dimensional space that captures its essential patterns with less complexity. The code evaluates the trustworthiness of a spectral embedding, which measures how well nearby points in the original high-dimensional data stay close after embedding. It uses Scikit-Learn's trustworthiness measure with the original features and embedded points, considering 12 nearest neighbors. The resulting score indicates how well the embedding preserves local data structure. The output checks the Scikit-Learn version for reproducibility, then reports the dataset shape before and after spectral embedding. This confirms that the original 3-dimensional data was reduced to 2 dimensions. It also shows a rounded trustworthiness score, which indicates how well the embedding preserves local neighborhood relationships. A new Matplotlib figure and axis are created to set up the plotting area. A scatter plot then shows the first two spectral coordinates, with each point colored by its position along the original curved manifold. The point size and Veritas color map help make the manifold structure easier to distinguish. The plot is prepared to show the spectral embedding of an S-curve manifold. It includes a clear title, axis labels for the first two spectral coordinates, and a color bar showing position along the original curved manifold. The visualization is then displayed for viewing. This script applies spectral embedding to a noisy synthetic S-curve dataset with 600 three-dimensional samples. It reduces the curved data to 2 dimensions to reveal the underlying manifold, then reports a trustworthiness score to show how well local neighborhoods are preserved. The resulting visualization colors the embedded points by their original position along the curve, helping show how spectral embedding captures nonlinear structure. Metric MDS. Metric multidimensional scaling, or metric MDS, turns pairwise distances into a 2- or 3-dimensional map. It places objects so that close pairs stay close and distant pairs stay far apart. Because it works from distances rather than raw features, it is useful when relationships between objects are the main information, such as travel times between cities or survey-based product dissimilarities. Metric MDS is a nonlinear visualization method that turns distance relationships in high-dimensional data into a spatial map. It can reveal patterns such as clusters, separations, and gradual transitions, whether comparing handwritten digits or patient clinical profiles. The axes themselves do not need a direct meaning. The main insight comes from how close or far the points are from one another. In metric MDS, the distance measure strongly shapes how well the plot represents the original dissimilarities. Euclidean distance is useful for standardized numeric data, but other data types may need different measures. Because reducing data to 2 dimensions can distort relationships, treat the plot as an approximation and check important patterns against the original data. Used carefully, metric MDS is a helpful tool for visual exploration and generating hypotheses. Python code, metric MDS. This example uses metric multidimensional scaling to map distances so that similar points appear close together. The resulting layout helps show how well the original distance relationships are preserved. We import key Python libraries for generating, analyzing, and visualizing clustered data. NumPy supports numerical array operations, Matplotlib creates plots, and Scikit-Learn provides tools for machine learning. In particular, we use a blob dataset generator, multidimensional scaling to reduce dimensions while preserving distances, and pairwise distance calculations needed for that process. We create a synthetic dataset with Scikit-Learn's makeBlobs function to test metric multidimensional scaling. The data contains 90 samples grouped into 3 clusters, with each point described by 5 features. A moderate cluster spread makes the groups distinct, and a fixed random state ensures the same data is produced each time. The function returns the data points and their group labels, which are used to evaluate how well the method maps the clusters into fewer dimensions. To standardize the data, we first find the average and standard deviation of each feature across all samples. Then we subtract each feature's average and divide by its standard deviation. This centers every feature around 0 and gives it a standard deviation of 1, so all features are on a comparable scale for later distance calculations. We compute Euclidean distances between every pair of observations using the scaled features. This produces a distance matrix that should be 90 by 90, matching the number of samples. If the matrix has a different shape, an error is raised to signal a problem in the calculation. We create a metric, multidimensional scaling model to project the data into 2 dimensions while preserving distance relationships as closely as possible. Because the distances have already been calculated, the model uses a pre-computed distance matrix, and a fixed random state makes the result reproducible. Applying the model with its fit transform method produces a two-dimensional embedding of the original data. To evaluate an MDS map, we compare the original pairwise distances with the distances between points in the two-dimensional embedding. We use only the unique distance pairs, excluding repeated values and the diagonal. The correlation between these two sets of distances shows how well the MDS layout preserves the original distance relationships. We first report the Scikit-Learn version to support compatibility and reproducibility. Then we check the metric MDS stress value, where lower stress means the reduced map better matches the original distances. Finally, we examine the correlation between original distances and MDS map distances to judge how well the distance relationships are preserved. Create a plotting area with Matplotlib, then use a scatter plot to display the two-dimensional embedding. The first embedding dimension gives the horizontal position, and the second gives the vertical position. Color each point by its label with the Viridis color map, and use a clear point size so the structure is easy to see. The code finalizes a metric multidimensional scaling plot by adding a clear title, labeling the two MDS dimensions, and including a legend to distinguish the data groups. It then displays the completed visualization for analysis. This script shows how metric multidimensional scaling maps high-dimensional data into two dimensions while trying to preserve distances between observations. It creates three synthetic clusters, standardizes the features, computes pairwise distances, and uses MDS to produce a two-dimensional embedding. The result is evaluated with a stress value and a distance correlation, and a colored scatter plot helps show whether the original cluster structure is maintained. Nonmetric MDS. Nonmetric multidimensional scaling is a visualization method for ordinal similarity data, such as rankings or preferences. Instead of preserving exact distances, it tries to place objects in a low-dimensional map so that the order of similarities is maintained. Items judged more similar appear closer together, making the method useful when relative relationships matter more than precise measurements. Non-metric, multidimensional scaling places data points in a low-dimensional map, so the order of their distances matches the original dissimilarities. It preserves which items are more or less similar, rather than trying to match exact distances. This makes it useful for subjective or uneven data, such as preferences, ecological comparisons, and psychological judgments, where the main goal is to reveal overall structure. When reading a non-metric MDS map, focus on which points are close together or far apart, not on the direction or meaning of the axes, since the map can be rotated arbitrarily. Clusters and separations can suggest similar preferences or related themes, but the display may distort complex relationships, depending on the chosen dimensions and starting setup. Use non-metric MDS mainly as an exploratory tool, and check its patterns with stress measures and domain knowledge. Python code nonmetric MDS. Nonmetric multidimensional scaling is used when dissimilarities are ordinal, meaning the rank order matters more than the exact distance values. The goal is to create a map whose distances preserve those original ranks as closely as possible. A useful check is to compare the original dissimilarity ranks with the distances in the map solution. We import the main tools needed for the workflow: NumPy for numerical operations, Matplotlib for plotting, and Scikit-Learn for machine learning utilities. From Scikit-Learn, we use tools to create synthetic blob data, compute distances between points, and apply multidimensional scaling to visualize high-dimensional data in a lower-dimensional space. We create a synthetic dataset with Scikit-Learn's makeBlobs function to test non-metric multidimensional scaling in a controlled setting. The data contains 60 samples grouped into 3 clusters, with each point described by 5 features. A moderate cluster spread is used, and a fixed random state makes the results reproducible. We first compute the exact pairwise distances between all data points, producing a distance matrix. These distances are then converted into ordinal dissimilarity ratings by scaling them relative to the maximum distance, mapping them onto a 0 to 5 range, and rounding up. The resulting coarse ratings are stored as floating point values for use in later processing. Set the diagonal of the ordinal dissimilarities matrix to 0, so each item is treated as perfectly similar to itself. Then verify that the matrix is 60 by 60, matching the 60 samples. If the dimensions are wrong, raise an error to catch the mismatch before continuing the analysis. We configure Scikit-Learn's multidimensional scaling to create a two-dimensional embedding from a pre-computed dissimilarity matrix. By using nonmetric scaling, the method aims to preserve the rank order of dissimilarities rather than their exact distances. Reproducibility and stability are supported with a fixed random state, multiple initializations, and convergence settings. The result is a lower dimensional representation that keeps the original ordinal relationships as well as possible. To evaluate nonmetric MDS, we compare the original ordinal dissimilarities with the distances between points after mapping them into the embedding space. We use only the unique pairwise comparisons, excluding repeated pairs and self-comparisons. The correlation between these two sets of values shows how well the mapped distances preserve the original rank order of dissimilarities. We first report the Scikit-Learn version to support compatibility and reproducibility. Then, we summarize the nonmetric MDS results using two key checks. Stress, where lower values mean the lower dimensional map fits the dissimilarity ranks better, and rank distance correlation, where higher values mean the map distances better preserve the original rank order. A scatter plot is created to show the two-dimensional MDS embedding. The first two columns of the embedding provide the point positions, while the labels determine each point's color, so clusters can be distinguished. A Viridis color map and moderately sized points make the cluster structure easier to see. The plot is finalized by adding a clear title, labeling the two MDS dimensions, and including a legend to distinguish the clusters. It is then displayed so the results of the nonmetric multidimensional scaling can be viewed in 2 dimensions. This script shows how nonmetric multidimensional scaling can map ordinal dissimilarities into 2 dimensions. It creates clustered data, converts pairwise distances into ranked dissimilarity values from 1 to 5, and applies nonmetric MDS to preserve their order. It then reports the software version, stress value, and rank distance correlation to assess the fit. A scatter plot of the embedding, colored by cluster, shows how well the original grouping is retained. t-SNE controls. SMACOF optimization. SMACOF is an optimization method used in multidimensional scaling to create nonlinear visualizations. It improves an embedding by repeatedly reducing stress, meaning it adjusts point positions so low-dimensional distances better match the original dissimilarities. Unlike t-SNE, which uses probability-based objectives, SMACOF focuses on preserving distances, so initialization, convergence, and repeated runs are important for reliable results. SMACOF creates a layout from dissimilarity data by placing similar items closer together and different items farther apart. It improves an initial rough arrangement by minimizing stress, but different starting points can lead to different results. Therefore, the final visualization is an optimized interpretation of the data, and its reliability depends on low stress and a stable configuration. SMACOF and t-SNE both depend on careful choices about initialization, updates, and when to stop iterating. In SMACOF, convergence is judged by whether stress stops decreasing meaningfully, while t-SNE relies on settings such as learning rate and iteration count. Poor starting points or too few iterations can produce misleading patterns, so it is best to run these methods multiple times and avoid overinterpreting small visual details. t t-SNE basics. t-SNE is a visualization method that turns high-dimensional data into a 2- or 3-dimensional map. Its main goal is to keep similar data points close together, making local patterns and clusters easier to see. This makes it useful for exploratory analysis, such as finding groups in images or biomedical data, and for revealing hidden structure that linear methods may miss. t-SNE creates a low-dimensional map by trying to preserve which points are close neighbors in the original high-dimensional data. Its heavy-tailed approach helps spread groups apart, making local clusters easier to see. However, the spacing, size, and position of clusters may not represent true global relationships, so t-SNE plots should be interpreted with caution. t-SNE is a tool for visualizing data by placing similar items near each other, such as songs with similar sounds or customers with similar habits. However, distances on the map should not be treated as exact measures of real-world difference, and the result can change with settings like perplexity and learning rate. Use t-SNE mainly for exploration, and confirm any patterns with domain knowledge and other methods. Python code, t-SNE basics. This example introduces basic controls for t-SNE. It focuses on how perplexity changes the neighborhood scale that the method emphasizes, and compares two deterministic t-SNE maps. We import key Python libraries for working with and visualizing data. NumPy supports efficient numerical operations, while Matplotlib creates plots. Scikit-Learn provides the handwritten digits dataset, t-SNE for reducing high-dimensional data for visualization, and Standard Scaler to standardize features so they contribute more evenly to the analysis. We load Scikit-Learn's digits dataset, a small built-in collection of handwritten digit images. It includes both the images and their labels, making it useful for quick experiments in classification, visualization, and dimensionality reduction. To make visualization faster and easier, we use only the first 300 samples from the digit dataset. This includes both the feature data and their matching target labels, giving us a smaller, manageable subset for quick exploration. The code validates the input data by checking that the feature table is two-dimensional and that the labels match the number of samples. If either check fails, it raises an error to signal that the data is not in the expected format. This helps ensure the data is ready for later processing. We standardize the features with Scikit-Learn's Standard Scaler, so each feature has a mean of 0 and a standard deviation of 1. This puts all pixel values on a comparable scale, which helps many machine learning algorithms work better. The fit and transform step computes the scaling values and applies them to produce the scaled data. We configure t-SNE to project the data into 2 dimensions, using a perplexity of 5 to balance local and broader structure. The learning rate is chosen automatically, and PCA initialization helps the embedding converge more efficiently. The process runs for 750 iterations, with a fixed random state of 42, so results are reproducible. This t-SNE setup reduces the data to 2 dimensions for visualization. It uses a perplexity of 40 to balance local and broader data structure, an automatic learning rate, and PCA-based initialization for a more stable starting layout. The model runs for 750 iterations and uses a fixed random seed of 42, so the results can be reproduced. We apply t-SNE to the same standardized features using 2 perplexity settings. A low perplexity map emphasizes small, local neighborhoods, while a high perplexity map shows broader structure. Comparing the two helps reveal how perplexity changes the data visualization. To compare 2 t-SNE maps in one plot, a copy of the high perplexity map is shifted to the right by a fixed gap. This keeps the original data unchanged while placing the 2 maps side by side. The separation makes it easier to visually compare how different perplexity settings affect the results. The code reports the Scikit-Learn version to support reproducibility, then explains that it visualizes a 300 sample subset of the digits dataset. It compares two t-SNE maps with different perplexity values, 5 on the left and 40 on the right, showing how neighborhood emphasis changes. Both runs use an automatic learning rate, PCA initialization, and up to 750 iterations. We create a Matplotlib figure and axes to set up the plotting area, then draw the first t-SNE map as a scatter plot. The points use the low perplexity map coordinates, are colored by their labels with the tab 10 color map, and are styled with moderate size and slight transparency for clearer viewing. The plot uses Matplotlib's scatter method to show the high perplexity t-SNE map. It places points using the map's 2 coordinate columns, colors them by digit label with the tab 10 color map, and uses moderate point size and transparency to make comparison with the other t-SNE map clearer. The plot separates 2 t-SNE maps with a gray dashed vertical line and labels each map by its perplexity value. The left map is marked as perplexity 5 and the right map as perplexity 40. A title explains that the comparison shows how perplexity changes the neighborhood emphasis in t-SNE. The plot labels clarify that the first t-SNE dimension has been shifted for comparison, while the second t-SNE dimension is shown on the vertical axis. A legend identifies the different digits in the scatter plot, making the visualization easier to interpret. The plot is displayed without stopping the script, with a short pause to ensure it updates properly. This script uses t-SNE to visualize a standardized subset of the digits dataset in 2 dimensions. It compares perplexity values of 5 and 40 to show how this setting changes the balance between local neighborhoods and broader structure. The 2 maps are plotted side by side, with points colored by digit label, making it easier to see how perplexity affects the resulting clusters. Perplexity learning rate. Perplexity in t-SNE controls the neighborhood size each data point uses when modeling high-dimensional relationships. Low perplexity emphasizes local structure, which can reveal small clusters but may split continuous patterns apart. Higher perplexity captures broader organization, but can smooth over fine details. Choosing perplexity is therefore a modeling decision about the scale of structure you want to study. In t-SNE, the learning rate controls how quickly points move as the map is formed. If it is too low, the layout may change too slowly and become cramped or unclear. If it is too high, points may overshoot and create distorted patterns. A well-chosen learning rate helps the visualization settle smoothly, so analysts often try several values to find stable patterns that reflect the data structure. When using t-SNE, tune perplexity and learning rate together, because both affect the shape and reliability of the visualization. Try several settings and look for neighborhoods or clusters that stay consistent, since these are more likely to reflect real patterns. Use lower perplexity for smaller datasets and consider higher values for larger ones, while adjusting the learning rate as the number of points grows. Focus on local neighborhoods, because distances between far-apart clusters in t-SNE are not always meaningful. Python code, perplexity learning rate. Compare t-SNE embeddings of handwritten digit data by changing perplexity and learning rate, since these settings affect how well local neighborhoods are preserved. Use trustworthiness scores to summarize and compare the quality of each embedding. This setup imports the main tools needed to visualize the handwritten digits dataset with t-SNE. NumPy supports numerical array operations, Matplotlib creates plots, and Scikit-Learn provides the dataset, version information, t-SNE method, trustworthiness evaluation, and feature standardization. Standardizing the data helps balance feature distances before applying t-SNE, while trustworthiness checks how well the resulting embedding preserves local structure. We load Scikit-Learn's built-in handwritten digits dataset to create a quick visualization example. The image pixel data is used as the features, and the digit identities are used as the labels. To keep the task efficient and manageable, we work only with the first 600 samples. Before running t-SNE, the code verifies that the number of feature rows matches the number of labels, so every data point has a label. If they do not match, it raises an error to stop the process. This check helps prevent problems during dimensionality reduction. We use Scikit-Learn's standard scaling method to normalize the dataset's pixel features so they have an average of 0 and a standard deviation of 1. This keeps feature scales balanced, which is important for t-SNE because it relies on distance calculations. As a result, no single feature dominates, helping produce better embeddings. 3 t-SNE settings are being prepared to compare how parameter choices affect the resulting embeddings. They vary perplexity and learning rate, moving from low values to higher ones, 5 and 50, 30 and 200, and 50 and 500. These configurations help explore which combination produces better embedding quality. We create 2 empty lists to track t-SNE results across different settings. One stores trustworthiness scores, which measure how well the lower dimensional embeddings preserve the original high dimensional relationships. The other stores the embeddings themselves, so different perplexity and learning rate configurations can be compared. The process tests several t-SNE settings by creating a 2-dimensional embedding for each one using the chosen perplexity and learning rate. Each embedding starts from PCA, runs with a fixed iteration limit and random state, and is applied to the scaled features. Afterward, a trustworthiness score based on 10 neighbors measures how well local structure is preserved, and both the embedding and score are saved for later comparison. To choose the best t-SNE setting, select the configuration with the highest trustworthiness score. The index of that top score identifies the matching setting and embedding, ensuring the chosen t-SNE result is the most reliable according to the trustworthiness measure. The code first reports the Scikit-Learn version to confirm the working environment and compatibility. It then introduces a comparison of t-SNE settings using trustworthiness scores, so the user understands the purpose of the results that follow. The code reviews each t-SNE setting alongside its trustworthiness score. It pulls out the perplexity and learning rate, then prints them with the score rounded to 3 decimal places. This makes it easy to compare how different settings affect embedding trustworthiness. A new Matplotlib figure and axis are created to prepare the plot. Then, a scatter plot shows the first 2 dimensions of the best embedding. Each point is colored by its digit label using a distinct color map, with modest point size and slight transparency to make overlapping points easier to see. The plot title highlights the best t-SNE settings by showing the perplexity and learning rate that produce the highest trustworthiness score. The axes are labeled as the first and second t-SNE dimensions, making the 2-dimensional embedding easier to interpret. The code creates a legend for the scatter plot, so each digit category can be identified. It sets the legend title to digit, lets Matplotlib choose the best placement, and uses a small readable font. The legend is then added to the plot, and the figure is displayed so the t-SNE embedding can be inspected visually. This script uses t-SNE to visualize a scaled subset of handwritten digit data and compare how different perplexity and learning rate settings affect the result. It creates 2-dimensional embeddings for 3 parameter choices, scores each one with trustworthiness to measure local structure preservation, and selects the best scoring configuration. It then reports the scores and plots the best embedding with points colored by digit label, helping show how t-SNE settings influence visualization quality. Embedding evaluation. Initialization stability. Initialization stability matters when evaluating manifold embeddings because nonlinear methods such as t-SNE can produce different maps from different starting points. A reliable embedding should preserve the main patterns across runs, even if the layout shifts, rotates, or stretches. If the same groups or regions keep appearing, the visualization is more likely reflecting real structure in the data, rather than random artifacts. To judge whether an embedding is stable, compare results across several runs with different initializations, including random and structured starts. The exact positions do not need to match, but important local clusters and separations should appear consistently. If a pattern, such as a rare patient subgroup, shows up repeatedly, it is more credible. If it appears only once, treat it with caution. Initialization stability helps distinguish real structure from random-looking patterns in a map. By comparing multiple runs, you can see which groupings consistently appear and which shift because they sit near boundaries in the data. The goal is to trust recurring relationships rather than exact shapes or distances. Used with measures like trustworthiness and comparisons to other methods, this makes evaluations more reliable and transparent. Python code, initialization stability. This example tests how stable t-SNE is under different initializations. Repeated runs should keep the most reliable local neighborhoods consistent, and trustworthiness provides a way to measure that stability beyond what the visualization looks like. We import the main tools needed for the analysis: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning utilities. From Scikit-Learn, we load the handwritten digits dataset, use t-SNE to reduce the data to 2 dimensions for visualization, and use a trustworthiness measure to check how well the embedding preserves local structure. We also standardize the features with a scalar, so they have zero mean and unit variance, which helps many machine learning methods work effectively. We begin by loading Scikit-Learn's built-in handwritten digits dataset. It provides digit images along with their labels, giving us the data needed for later exploration and visualization. The code uses a fixed subset of the digits dataset to make t-SNE runs faster and easier to compare. It selects the first 300 samples, including both their features and labels. Using the same smaller set each time keeps the results consistent across repeated embeddings. The code validates that the feature data has the expected 2-dimensional table shape, and that its row count matches the number of labels. This ensures each set of features has a corresponding label. If either check fails, it raises an error to prevent analysis with misaligned data. First, we standardize the features with Scikit-Learn's standard scalar, which centers the data and scales it to unit variance. This is important for t-SNE because it relies on distance calculations and is sensitive to feature scale. Standardization helps each feature contribute more evenly before the neighborhood analysis. We configure t-SNE to reduce the scaled data into 2 dimensions. A perplexity of 30 balances local and broader structure, while the automatic learning rate and random initialization guide the optimization. The run is limited to 750 iterations, and a random state of 42 makes the result reproducible. The scaled features are then transformed into a 2-dimensional embedding. This setup creates a 2-dimensional t-SNE embedding to visualize high-dimensional data. It uses a perplexity of 30 to balance local and broader structure, an automatic learning rate, and random initialization, with 750 iterations to seek a stable result. A fixed random state makes the run reproducible, and the transformation is applied to standardized features so t-SNE can work effectively. The code evaluates the trustworthiness of 2 t-SNE embeddings, A and B. Trustworthiness measures how well nearby points in the original high-dimensional data stay close in a lower-dimensional embedding. Using the scaled features and 10 nearest neighbors, it compares both embeddings to assess how well they preserve local structure. The output reports the Scikit-Learn version to support reproducibility, then shows the trustworthiness scores for 2 t-SNE runs, rounded to 3 decimals. These scores indicate how well each embedding preserves local neighborhoods from the original data. When judging stability, focus on recurring digit neighborhoods across runs rather than the exact plot axes. A scatter plot is created to visualize the t-SNE embedding, with the first embedding dimension on the x-axis and the second on the y-axis. Each point is colored by its label using a categorical color map, with moderate point size and slight transparency to make overlaps easier to see. This helps reveal the neighborhood structure in the embedded data. The plot is prepared to show a t-SNE visualization of recurring digit neighborhoods, with labels for the 2 t-SNE dimensions and a legend identifying the digits. It is displayed briefly without stopping the script, then closed afterward to free resources. This script tests how stable t-SNE results are when the random starting point changes. It loads and scales part of the digits dataset, then creates 2 two-dimensional embeddings using different random seeds. For each run, it measures trustworthiness to see how well local neighborhoods from the original data are preserved. It prints the 2 scores and shows one colored plot of the embedding, focusing on whether similar digits cluster together, rather than on the exact plot axes. Trustworthiness score. A trustworthiness score measures whether a low-dimensional embedding preserves the original data's local neighborhoods. Methods like spectral embedding or t-SNE can make unrelated points look close, so the score penalizes these false neighbors. A high score means nearby points in the visualization were also similar in the original space, while a low score warns that the apparent structure may be misleading. The trustworthiness score shows how well an embedding preserves nearby relationships, with higher scores meaning fewer misleading neighbors. Its meaning depends on the neighborhood size. Small neighborhoods test very local structure, while larger ones capture broader patterns. Choose the neighborhood size based on your goal, and consider multiple sizes when you need to evaluate both detailed clusters and wider category relationships. Trustworthiness is helpful for judging embeddings, but it should not be the only measure of quality. It mainly checks whether a visualization creates false neighbors, not whether it preserves all real neighbors, global distances, or cluster sizes. Because methods like t-SNE and MDS can emphasize different structures, trustworthiness should be combined with visual inspection, domain knowledge, and stability checks to avoid mistaking misleading patterns for meaningful ones. Python code. Trustworthiness score. Use a trustworthiness score to compare embeddings by checking whether nearby points remain reliable after visualization. Higher scores indicate that the local neighborhoods in the embedding are more trustworthy. We import key Python tools for analyzing and visualizing the handwritten digits dataset. NumPy handles numerical arrays, Matplotlib creates plots, and Scikit-Learn provides the dataset and machine learning utilities. Multidimensional scaling reduces the data for visualization. Trustworthiness checks how well local relationships are preserved. And Standard Scaler standardizes features so they contribute evenly. We load a small handwritten digit dataset from Scikit-Learn and use only the first 300 images to keep the work manageable. For these samples, we also keep the matching labels, which identify the digits shown in each image. This creates a compact dataset for later analysis and visualization. Before creating embeddings, the code verifies that the number of feature rows matches the number of labels. This ensures every data point has a label. If they do not align, it raises an error to stop processing and protect data integrity. We standardize the feature pixel values so they are on a similar scale. A standard scaler is fitted to the data and then used to transform it, giving each feature a mean of 0 and a standard deviation of 1. This helps many machine learning algorithms work better by preventing features with larger scales from dominating distance calculations. To visualize high-dimensional data, multidimensional scaling is configured to reduce the scaled features to 2 dimensions. A fixed random state makes the result reproducible, and automatic normalized stress helps manage the optimization. The fitted transformation produces a 2-dimensional embedding that makes relationships between data points easier to inspect. We use the trustworthiness score to evaluate how well a 2-dimensional embedding preserves local neighborhoods from the original high-dimensional data. Calculating it with 5 neighbors checks very local structure, while using 20 neighbors gives a broader view. Higher scores mean the embedding is more reliable for representing neighborhood relationships. The code reports the Scikit-Learn version to help confirm compatibility, then prints trustworthiness scores for embeddings using 5 and 20 neighbors. These scores show how well the embedding preserves local data structure, with higher values indicating better preservation. The results are rounded to 3 decimal places for readability. We create a scatter plot of the 2 embedding dimensions using a 7 by 5 inch plotting area. Each point is colored by its digit label with a distinct color map, making the groups easier to compare. This visualization helps relate the trustworthiness score to the actual structure of the embedded data. The plot is titled as an MDS embedding of handwritten digits, making clear what the visualization represents. The horizontal and vertical axes are labeled as the first and second embedding dimensions, helping viewers interpret the 2-dimensional scaling space. The code creates a legend for the scatter plot, using the plotted points, labels it by digit, and lets Matplotlib choose the best location. It then adds the legend to the plot and displays the final visualization, making it possible to inspect the embedding of the handwritten digits. This script uses multidimensional scaling to reduce scaled handwritten digit data to 2 dimensions for visualization. It measures trustworthiness with 5 and 20 neighbors to check how well the embedding preserves local relationships. Higher scores mean the 2-dimensional view is more reliable. The final plot colors points by digit label, helping assess how clearly the digits cluster and separate. Method comparison. When comparing manifold embedding methods, do not judge them only by how the plot looks, because each method preserves different structure. Spectral embedding emphasizes connectivity. Multidimensional scaling preserves broader distance relationships, and t-SNE focuses on local neighborhoods that often appear as clear clusters. The best choice depends on the question. t-SNE may separate digit classes well, while multidimensional scaling may better show subtle similarities between shapes such as 1s and 7s. When evaluating manifold embeddings, combine quantitative scores with visual inspection. Trustworthiness shows whether local neighborhoods are preserved, but it does not guarantee that the overall structure is reliable. Visual checks can reveal whether clusters, transitions, outliers, and known labels make sense. If a pattern appears only under one t-SNE setting, treat it as a lead for further investigation, rather than a confirmed discovery. To compare manifold embeddings reliably, apply methods such as spectral embedding, multidimensional scaling, and t-SNE under the same preprocessing and consider the assumptions each one makes. If several methods reveal similar separations, the pattern is more likely to reflect real structure in the data. When they disagree, the differences can still be useful because each method may preserve different relationships, such as local neighborhoods, branching patterns, or broad continua. The goal is to judge what each embedding preserves or distorts, so the results support sound analysis and decisions. Python code. Method comparison. Use a neighborhood metric to compare embeddings and assess how well they preserve local structure. Trustworthiness measures this preservation, while the visualization highlights differences between methods. We import key Python libraries for analyzing the handwritten digits dataset, NumPy for numerical arrays, Matplotlib for visualization, and Scikit-Learn for machine learning tools. From Scikit-Learn, we use dimensionality reduction methods, including multidimensional scaling, spectral embedding, and t-SNE, along with a trustworthiness measure to evaluate how well each embedding preserves local structure. We also standardize the features, so distance-based methods treat them more evenly. We load Scikit-Learn's built-in handwritten digits dataset and use only the first 300 images. For each sample, we keep the pixel data as the input features and the matching digit label as the target. This smaller subset makes it easier to analyze the data and compare embeddings. The code first verifies that the feature data has 300 rows and 64 columns, meaning it contains 300-digit images with 64 pixel features each. If the dimensions are wrong, it raises an error instead of continuing. This check helps ensure the data is correctly formatted before fitting the embeddings. We first standardize the features using Scikit-Learn's standard scaler, so each feature has a mean of 0 and a standard deviation of 1. This is important for distance-based methods because it puts all pixel features on the same scale, making distance comparisons fair. We configure 3 embedding methods to project the data into 2 dimensions: spectral embedding, multidimensional scaling, and t-SNE. Spectral embedding uses a fixed random state for reproducibility, while multidimensional scaling uses automatic stress normalization with a single initialization for efficiency. t-SNE is set with a perplexity of 30, automatic learning rate, PCA initialization, and up to 750 iterations. Together, these settings create comparable 2-dimensional views of the data. We compare 3 ways to reduce the same scaled high-dimensional data into 2 dimensions: spectral embedding, multidimensional scaling, and t-SNE. Spectral embedding captures the main structure, multidimensional scaling tries to preserve distances between points, and t-SNE focuses on keeping nearby points close together. Using the same preprocessed data makes the comparison fair. We compare spectral embedding, MDS, and t-SNE by measuring how well each one preserves local neighborhoods from the original scaled data. Using the trustworthiness measure with 10 nearest neighbors, each reduced embedding is scored against the original features. These scores show how accurately each method keeps nearby points together after dimensionality reduction. The code reports the Scikit-Learn version to support compatibility and reproducibility, then prints trustworthiness scores for spectral embedding, multidimensional scaling, and t-SNE. These scores show how well each method preserves local neighborhood structure, making it easier to compare the quality of the embeddings. We collect the embedding method names, including spectral, MDS, and t-SNE, along with their trustworthiness scores. These scores show how well each method preserves the local structure of the original data after embedding. Organizing them together prepares the results for a side-by-side comparison in a visualization. The process measures how widely each embedding method spreads its points in 2 dimensions. For the spectral, MDS, and t-SNE embeddings, it calculates the standard deviation in each dimension, averages those values into one overall spread score, and stores the result. These scores can then be compared to see how differently the methods distribute their points. The spread values for each embedding are normalized by dividing them by the largest spread, making the methods easier to compare on the same scale. Then, x-axis positions are created, so each embedding method can be shown as a separate bar in the plot. This plot compares embedding methods using 2 side-by-side bar measures, trustworthiness and relative spread. The chart sets method names along the x-axis, uses a shared score scale from 0 to just above 1, and labels the axes clearly. A title and legend explain the comparison, and the plot is then displayed for easy visual evaluation. This script compares spectral embedding, multidimensional scaling, and t-SNE on a scaled subset of the handwritten digits dataset. Each method reduces the data to 2 dimensions, then is evaluated by trustworthiness to measure how well it preserves local structure. The script also compares the relative visual spread of the embeddings and shows both measures in a bar chart, helping summarize how the methods differ in structure preservation and spread. In this lecture, you learn to apply spectral embedding and MDS methods for nonlinear visualization, configure t-SNE perplexity, learning rate, initialization, and convergence settings, and evaluate manifold embeddings using trustworthiness and visual comparison. In the next module, Module 26, we will go over mixtures outliers.
Thank you for your attention. See you all in the next lecture.